All right, we can go ahead and get started then. So it's nice to be here. Nice to see everyone. Some familiar faces and good friends and folks who I don't know yet. Present and future friends. So nice to meet you all. This is for slides online later. I will share these slides. There's a QR code at the end. And I'm also really interested in your feedback. So I have a QR code for a SurveyMonkey survey at the end. I really appreciate when people tell me how to get better. So, this is just a general table of contents for today. There's a whole bunch of stuff here that I've kind of tried to structure. Part of the reason that I'm interested in your feedback is that this is all kind of taking shape and has taken shape over the last, well, really over most of my career, but it's an evolving kind of coalescing performance method and set of ways to think about performance, monitoring, how to observe things and how to fix them. And so I'm starting to sort of feel like it's gelling into something that I might publish in different formats. So this is like my overall philosophy. So the first topic is quality of service. And in any service, whether it's a database or something else like a network attached service API type of a thing, the most important thing about that service is the quality of service that it's giving to its customers. Those might be human users or they might be another service that's making calls to it. For a database, obviously most of the time the customer is an application. And then there are customers of that customer and so forth. But really having a customer-centric view is so important. And therefore, quality of service is the most important thing to measure about your database. There are lots of things that you could measure. As you know, if you've looked at the status variables or any of the other ways that you can measure things about your database, there are hundreds and hundreds of things that you could measure. And so one of the big questions is, what should I measure? What should I monitor? And my answer is, first and foremost, you should measure quality of service. And that's because your database's job is simply to do queries for somebody or something. And what that somebody or something cares about is performance from their perspective. So from the machine operator's point of view, we often think of performance in other terms, but from the customer's point of view, I asked a question, made a query, sent a request, whatever the terminology is. I asked that service to do something for me, and I care that I get the answer and get it correctly and fast. So those are, that's how, as a user or a customer of that service, I define the quality of that service. So that means that we need to measure requests, queries, calls, whatever the terminology is. And another way that I put this is measuring work getting done. Our service exists to store data. Our database exists to store data and do useful work, and so we need to measure the useful work getting done. So quality of service from the user's perspective is, I sent a request, I want a correct reply fast, and the definition of that is latency. How long did it take for my answer to come back? And I'll use some terms like latency and so forth in here. I don't know if they're familiar to everyone, but they're widely used in the performance literature and theory, and so I'm trying to stick with the sort of well-defined and familiar definitions that you'll find elsewhere. So latency is really how fast the request is, and it's the time that elapses from when the request begins to when it ends. Sometimes in other places you might see latency defined a little bit differently, like how long it is before the request gets started to work on. Those are kind of, people use these terms in different ways sometimes, but generally most of the time people will talk about latency as being from the request starts to when it finishes, rather than how long it waits before it gets started. Okay? And so this is the user's perspective. So we're really caring about the user or customer's perspective. And this is one user, one customer. So suppose I'm using a service like Twitter. I am the only person that I care about when I'm posting a tweet. I know that there are lots and lots of people who are tweeting out there, and I hope that they also get a good experience, but what I really care about is my experience, not everyone else's tweeting. So this is a very unambiguous definition of performance. I don't have to describe it in analogies or anything like that. This is something that we can measure very precisely. As a service operator, as a database administrator, as a DBRE or SRE or whatever the term, whatever your title says, you don't get the luxury of caring just about Baron and Baron's tweets. You have to care about all the people who are trying to tweet and their performance. And as soon as you go from one to many, you have a problem because you need to have a singular definition of performance and quality of service, not 30 million or whatever the current number of people trying to tweet is. And so it needs to be reducible down to singular metrics, a small set of singular metrics. So it's a population, a description of the population's collective experience. And any service that's really, most of the time, any service that's useful in the context that we care about is going to be multi-user. It's not going to be, it's not going to have a single customer. So we almost always have to care about a population and their entire experience as a whole. So that workload quality of service, that set of requests that's coming from that population is what we call the workload. That's the totality of all the work that our database is doing. And the workload quality of service is what we care about characterizing and understanding in order to optimize database performance. So it's the set of interactions between the set of users and the database, and it's really measuring across the boundary between the users and the database. That's the workload crosses over that boundary. So it turns out that through a whole bunch of theory and practice, the best set of definitions of workload quality of service boils down to 4 things. And the only acronym, the only word that you can make out of the initials of these 4 things is KELT, unless somebody knows of another acronym that I'm not aware of. And so these 4 metrics actually give a very good description, a complete and mathematically valid and useful description of workload quality of service. Bless you. So concurrency is the number of simultaneous requests at a time. So if there are, what do we have, maybe 60 people in this room. This room has a concurrency of 60 right now, and it changes a little bit. Somebody just came, welcome. So now we have more than we had a moment ago. Here comes the door. Thankfully, nobody is leaving. So the number of things that are happening at a moment in time, or the number of things that are present in the system at a moment in time, is concurrency. And we're measuring requests. So if you take a snapshot an instant in time and just see how many requests are resident running, that's your concurrency. You can also average this over a period of time. For example, over a period of time, like the duration of this talk, we could have an average of the number of people that were in this room. So concurrency can be both an instantaneous and an average metric. The error rate is the number of requests that don't complete successfully. And I don't know what the analogy would be for this room. I'm inventing this analogy on the fly, so I think I've probably overplayed its usefulness. The latency we previously discussed, and throughput is number of requests per unit of time. So this one, there is no instantaneous latency, there is no instantaneous throughput. These are only valid over windows of time, an observation window. And I put the typical mathematical indicators of these at the end. We won't do any math in this talk, but if you're looking at Little's law, for example, usually throughput is X, concurrency is N, response time is R, latency, residence time. Sometimes these things have synonyms, but usually people use R to denote the latency. So for characterizing the workload quality of service, the whole population over some period of time, aggregate metrics like average are one way to do it. Another way to do it is to use a long tail metric like the 99th percentile. If you're not familiar with percentiles, basically what you do is you take a set of things, like a whole set of requests and their latencies over a period of time. You throw away the top 100, or sorry, you throw away the top 1%. And then the metric of the largest thing that remains is your 99th percentile latency. So it's a measure of how some of the time people have an extremely long response time. And it gives you a good sense of what kind of experiences your users might have on occasion, which is really much more important than the average, which can hide. Averages get badly skewed and they hide outliers. Percentiles and medians and things like that are a little bit more resistant to getting skewed by outliers. So they can give you a better indication of sort of a typical type of experience that your user base is having. This is the only math, I think, in this talk. Trying to remember if I put any other equations in here. Because I mentioned Little's Law, and you saw those N, R, and T. And there's a really useful relationship among those three called Little's Law. And I haven't shown Little's Law here in the main part, but up in the sentence, N equals XR is Little's Law. And if you do a little bit of derivation of that, you realize that you can get concurrency out of, basically, of those three factors in Little's Law, you can take any two and calculate the other one, just sort of like if you have two angles or sides of a triangle, you can get the third. And similarly, if you measure a whole bunch of latencies and then divide the observation divide by the length of the observation interval, you also get concurrency. So there's a couple of different ways to get concurrency. And concurrency is super, super useful because it is the single best indicator of the amount of work or service demand or load that your system is doing. And when you think about like load average in a Unix system, it's essentially concurrency under a slightly different shape. A lot of the things, you think about backlog, if a metric is called backlog, like disk queue backlog or things like that, queue length, there's a whole bunch of different names for things that are indicators of load, and they all come down to concurrency in one way or another. So you're already familiar with this concurrency, just probably under different names in different places. So I said earlier that performance from the user's perspective is, I sent you a request, I just want it back fast. But when we think about system performance or database performance, we're often used to thinking about other things like CPU load and how much memory is free and things like that. And so the question comes up, are those things not useful definitions of performance? You know, should I ignore those? Do I only have to care about those KELP metrics? And the answer is no, these are also useful and interesting. It's just that they are not really the user's perception of performance. So what we're starting to draw out here is that there's both a user-facing perception of performance, what matters to users, and then there's also something else that matters, but it's not necessarily something that users care about. Back to my Twitter analogy, I know Twitter has CPUs and disks, and I know they're full and busy and things like that, and I just don't care. That's their job. And I'm really grateful that there are people who are making sure that there's enough CPU and disk and network bandwidth and things like that to get my tweets posted, but it's not my job to care about. But it is our job as people who are operating these services, and so we do have to measure and care about these things, and they are useful and good indicators. They're just not necessarily what users care about. So again, if we think about work getting done, this is the resources that are required to get work done on behalf of your users, but it's not the performance of the work itself. So these resource metrics can be categorized into four. You could collapse a couple of them in. You could collapse storage and network into I/O. But I like to think of them separately because storage and network typically are, separate subsystems and through separate hardware and things like that. So these four, CPU, memory, network, and storage or disk, are your typical resources that you care the most about. And then I'll talk a little bit later about the sharp corners of the technologies that you're working with, and there are particular technology-specific resources that you care a lot about, like thread pools and connection pools and those kinds of things. But in the sort of first cut of the most generic, most useful things that we look at on a system level, internally, inside the service, these are kind of the big four. And the question is, well, how do we know if those are adequate? Do we have enough sufficient resources to serve our workload? And there's a really nice model that Brendan Gregg has developed called the use method, which is actually a performance troubleshooting method to help somebody rapidly orient themselves and drill into a system that is performing poorly and figure out where the bottleneck might be. And basically, you take every resource in the system or every component of the system, and you look at, is it utilized? How utilized is it? Is it saturated, and is it throwing off errors? And if you follow this link, grab the slides later and follow this link, Brendan has an entire web page about this with an enormous list of different services, technology specific, operating specific, and for each of those, he gives you some guidance on here's how to apply the use method to those. You know, here are the components, here's how they're wired together, here's how to find utilization, saturation, and errors in them. So a super, super helpful performance troubleshooting method when things are overloaded and not working well, but also a very good mnemonic for understanding whether these resources are sufficient to handle the workload. So this is an additional 3 set of letters, one of them E, we see duplicated. And if we put those together, we get what I call the totality, holistic view of the system. And I haven't found a better analogy than the Zen Yin Yang symbol yet, but I'm sure there is one out there because this is not a religious talk, but these two things do fit together really nicely. So first, we have these KELT metrics that are external facing quality of service. And then we have the internal, we've got these resources, and are they in trouble? Are they sufficient? And when you look at those things together, you actually see, outside of and inside of that boundary, that the application or user boundary, that the workload flows across to the service and back. So we put those two together and we get 7 golden metrics. And I'm borrowing a little bit from site reliability engineering terminology here. The SRE book has what they call 4 golden metrics. I think this is a little bit clearer than the 4 golden metrics. In talking with people, I found that it's often very difficult for them to understand the difference between some of the SRE golden metrics, like what do they exactly mean. And I think that these are a little bit clearer. I'd love to hear your feedback on that again. So this, I think, is how we can characterize a system really completely. Now, when I say system, sometimes I use that to talk about a computer or a database or something like that. But usually I'm thinking about both the computers and the database and the network, as well as the user population. So I'm trying to think about it all together, and that's what that Zen yin-yang symbol is trying to indicate, because these things are all interdependent and interacting with each other. In reality, when I click to tweet, I'm not tweeting in isolation. My tweet has to go into a queue, and if a whole bunch of other people are tweeting at the same time, I end up waiting for them, whether I know it or not, or I'm making them wait for me, or whatever. We're all interacting with and impacting each other, and impacting sort of through the medium of these systems that are serving our request. So there's a whole big thing, a whole big ball of spaghetti that you can't just pull apart and look at any single part in isolation, because its behavior is dependent on the behavior of everything else in the system. So that's why I think the holistic viewpoint over these systems is really important, because if you're looking only at things like CPU and disk utilization and things like that, those are valuable signals, but you can have entire blind spots that you're not aware of at all. And if you're looking only at the external facing, how's the user's perspective of performance, are they satisfied or dissatisfied, then you're missing the explanation for why. If the CPU is full and you don't know that, then, or if there's another query running on the system, if the backup job kicked off and you can't see that. And this is a slight tangent here, but this is one of the reasons why a lot of times when you have application-specific monitoring, you can see problems happening in the application, but you can't really explain them unless you're looking at the things that the application depends on, like the database. And if the backup kicked off and the database is slow, or if there's another service that talks to that same database and is doing something abusive, that might be the explanation why a particular service is suffering. And so you have to be able to see all of those things together to be able to see the whole picture. So this gets to mental models. So when we talk, I described, me and all of the 30 million people trying to tweet and all of the servers inside of Twitter and the networks and things like that. What I'm describing is how I conceptualize the whole tweeting system, the entirety of all the users and the computers and networks and everything. And that's just my model, and I think it serves for this talk, but it's not accurate. It's really not accurate at all. I don't understand anything And in fact, most of us don't really understand even the code that we wrote ourselves. So we have this system as we imagine it in our heads, this construct that helps us to do useful things and to predict how this code that we write is going to behave, or to predict, I'm going to change a configuration parameter in the database. How do I think that's going to change it? And we're always slightly wrong. And you can see that even in really simple systems. So this is, Pete Holiday tweeted this at one point, and I thought it was great, so I just screenshot it. A 5-line for loop is going infinitely, and this is somebody who's pretty experienced, and I empathize with this. I haven't been programming for quite a quarter century, almost that long, I guess. And I've definitely had 5-line for loops go infinitely, or off by 1 or whatever. And I'm staring at it, and I can't figure out why. And really, the way that I solve this most of the time is I start the debugger, and I go one step at a time, or I get my rubber duck next to me, and I explain it to the rubber duck. And suddenly I realize, oh, I wasn't understanding this code correctly. Of course, the code is behaving exactly as the code behaves. It's me who's at fault, right? But so we have these mental models about everything that we operate, everything that we build, everything that we try and debug, and they're always slightly wrong. And one of the really cool things about being able to measure and observe them more accurately is that it shows you where you're wrong. And that's an opportunity to learn, to improve, and to understand your system better. So, I talked about, the service that is suffering because the backup job is running on the database. Well, all of these bullet points on this slide are things that I have seen either myself or at customers of VividCortex. I didn't give you an introduction, but VividCortex is a database monitoring system. And a bunch of these stories come directly from working with customers. And I could fill page after page with stories like this, right? So, the first one, I went to a customer and we put a profile. I'll show you a profile later. Put a profile up on the screen. And it was a room full of developers, some of them working on very specific parts of the code, some of them who were kind of the senior people who knew everything about the code, and they knew all the skeletons and all the closets. And the one guy kind of had his head tilted to the side a little bit. You know how people do that. And so I stopped and said, you look like something on the screen doesn't look right to you. And he said, yeah, that number 1 query at the top, talk to me about that a little bit. And I said, well, blah, 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 the technical explanation of what we're seeing on this screen, blah, blah, blah. There's like 4 copies of that query running all the time on average, concurrently 4. And he goes, whoa, no, that's not the way that query runs. I know that query. I wrote the system that does that. It purges the data every morning. It takes like a minute. There shouldn't be 4 copies of that query running. And this was the moment of surprise when we realized that our mental models about how this system was built had some flaw. Reality and the mental model were a little bit different. And I said, well, there's probably something really interesting here. I mean, I don't know. I'm not the developer, and I don't know where this code lives and runs, but there's probably something really interesting here. And a couple of minutes later, he started working on his laptop. A couple of minutes later, he goes, I got it. He said, I forgot to put the where clause on the daily purge job. So yeah, I wrote that purge job years ago, and in the beginning, it was only doing a day. On the second day, it was doing 2 days. 4 years later, every morning, it's archiving all 4 years of history. So and it's taking 4 days to run. So that explains why it's running 4 copies at once. So he put the where clause on till the minute to the last day, and solved that problem. So there are always these kind of surprises, and then some kind of enlightenment follows. But the only way to get this is to measure and then refine that mental model to show us the difference between reality and how we think things really are. All the rest of our mental model and my speculation about how Twitter works and things like that, that's all just imagination. So it might be good imagination, it might be accurate imagination, but often it's not. So back to the question of workload quality of service. When we monitor our system, super important to monitor the workload and how customers are experiencing, because a lot of the big surprises are to be found there. Okay, so how to measure workload? There's a handful of ways to do that. and they're all request oriented. So first you can turn on query logging, and now I'm going to start getting a little bit database specific. So first you can turn on query logging. The good thing about this is that basically every database has a way to log all the queries. So you can do it. It is possible to do this. It often has a pretty high performance overhead, so that's kind of the downside of it. And now you also have to think about things like safety and security. So safety, like, am I going to fill up the disks and crash the servers? And security, do I now have sensitive information logged somewhere that I'm in violation of our compliance requirements? And on a busy database server, this performance overhead of logging it is one thing, but then the performance overhead of analyzing it is another. And in a lot of systems that I've worked on, you couldn't do the analysis. Like, you couldn't run PT Query Digest on the server that you were logging on because it consumed too many resources. You had to copy it onto another server. So it's kind of, this is a slow way to get insights into the query workload, but it does work. The second one is to use internal statistics. This is great if it's built in. It's often a relatively low overhead way to do. It's often a little bit less granular insight into the query workload as well. It's often pre-aggregated, so you can't do things like get percentiles. You can only get totals and divide them by each other to get averages, things like that. And sometimes it's either not enabled or it's not a feature in that database technology yet. So I think probably all of us have come up through times when our database of choice didn't have any performance schema or PGStat statements or MongoDB profiler or whatever, So we probably have those before and after memories. And we're probably still working with some databases or data technologies that don't really yet. Like, how do you ask Kafka what its whole workload is? So there are technologies that don't have this in the beginning, and later they add it. Usually they'll add a query log or some kind of a workload log in the beginning, and then later they'll add these internal statistics. One that I love very much and find really useful is sniffing the network traffic, because the traffic is typically crossing over the network boundary, and so you can observe it there. This is front and center to how the Cortex works. So we just reverse engineer the protocols of the databases, and we time the queries as they go across the wire. So you can get complete insight into everything that's happening from the network level that way. And there are lots and lots of technology. You can do this with Wireshark or TCP dump. You can do it with Vivid Cortex. There are lots and lots of other sniffing technologies out there. So it's a widely used way to do it. Okay, so this is how to measure, and it's what to measure and how to measure. And now we get into performance problems. So we have this data. Now how do we use it to do useful things? So the useful things typically involve solving problems. So in my usual reductive way of turning things into lists, I'm going to make a list of the types of performance problems and then look at the types of solutions and tools for each of those. So there are basically three kinds of performance problems that you will run into, categories of performance problems. So the first one is something that users care about, that latency is too high, either of individual requests or of, like the P99 request latency or something like that is too high. It's over the SLAs or SLOs, or it's just a bad experience for a user. And sometimes you don't need to measure that to know it. The second one is that you don't have enough resources, or resources are insufficient to do the workload, so you just have a load problem. And the third one is that you have some interaction between different systems that are sharing some kind of a resource. So you have the noisy neighbor problem, often solved by killing your EC2 instance and restarting it elsewhere. Whatever, but there are lots and lots of different kinds of noisy neighbor problems, but they're all essentially similar. That there is a fixed set of resources that's being divided across lots of users, and somebody is hogging too many, and someone else is not getting enough. So these causes of performance problems come from things like an application making requests that actually serve no purpose and can be eliminated without impacting correctness or usefulness, making requests too frequently, making them too slowly, or making requests that are going to be too slow because of the way that they're written or designed. Or we have these resource starvations or system stalls. And when systems get overloaded, they tend to get very irregular. And there's a whole bunch of math behind why, but basically systems get really nonlinear as they get under a lot of load. And so they can either get slow when they're under a lot of load, but more often what you'll see is things completely becoming unresponsive for periods of time. And those look like complete stalls. They're not typically complete stalls. There's something doing some work somewhere and everything else is stalling. But from the perspective of, is my system doing its job, it often looks like a complete stall. So the performance Swiss Army knife that can help you find more of these problems than any other and solve more of them than any other is a profile. And basically what you do is you break apart your workload into categories, and then within each of those categories, you just rank them. This is a screenshot from VividCortex. I'll have it bigger on the next slide. So you group them together in categories, and then you just rank them in descending order. So this is a bigger view of the same screenshot. Designs are different from product to product. You'll see these in New Relic. You'll see them in command line tools like OProfile. Maybe they don't have visuals. Maybe they just have numbers. You can do this with sort minus rn at the command line. There are lots and lots of ways to generate profiles, but the characteristics that they have in common is this breakdown and then ranking of the breakdown. So VividCortex does this visually and numerically. If you look at the left-hand column, you see those little blue underbars. Those are basically a percentage of the total. If you sum all those blue bars up, they will equal the width of the column. The big numbers like 28.89% in the top right, that's the same number as the blue bar as a percentage. And then we have a visual of how that changes over time, because that single number doesn't tell you whether this was smooth or spiky or whatever, so you can see whether it was smooth or spiky. And then we add more columns in like count and average latency and things like that. And you can see, this one has high average latency. The second one up there is relatively frequent. So you can kind of look at this and get a lot of information about this workload from several dimensions at once. So that's the usefulness of a profile. It helps you prioritize and focus. So it helps you to answer questions that'll solve these various categories of performance problems. So let's go through those categories and look at how a profile can help you to address each of those. So if you have needless and too frequent requests, you just profile by frequency. Here I was profiling by the most time-consuming, so the sum of the latencies, which is from earlier. It's the same as the concurrency. So just basically profiling by total time consumed or most time-consuming is profiling by the most load-creating. If you're looking for needless requests or requests that are running too frequently, you just profile by the count, by the frequency. And then you rank by the sum of the count. And you can look at this a lot of times. This is one of the cool things that you can find when you're doing network sniffing. You'll see things like ping or set names UTF-8 or a lot of things that are either language specific or driver specific or application framework specific. And a lot of times they're often just junk, like a connection pool management that does a ping every time it gets a connection from the pool to see if the connection is alive. That's ultimately a useless query because you could just send the query, and if the connection is dead, the query will fail, and then you can get another connection or open another connection and do it again. And drivers or application frameworks are very different in this. Ruby on Rails loves to do ping. PHP loves to, when it's connecting to MySQL, it loves to set names UTF-8 and a whole bunch of other stuff every time. And a lot of times that stuff isn't necessary at all. So surprisingly, or perhaps surprisingly, oh, and another big one is commit when you haven't begun. When you're in auto commit mode and you do a commit anyway. And surprisingly, a lot of times these things add a ton of load. And you don't know that unless you measure it. I mean, you wouldn't think that a commit that is a no-op would cause a lot of load. You wouldn't think that a ping would cause a lot of load or latency. But when you measure it, there's our difference between our intuition and our mental model. You'll often see that it actually makes a huge difference. So when you eliminate those ping queries, you can see the impact in resource consumption on the box, for example, on CPU consumption. And you can see the impact in not just the end user response time at the application level of getting the answer without doing a ping first, but you can also see the impact on useful queries latency because the database server has less work to do. So it's often surprising how much performance you can gain from doing this. To find requests that are too slow, you profile by the sum of latency, and then you can look at outliers. I showed you on the previous slide here. Here's an outlier. This one has a high average latency. So we should probably look into that one and see why is this one 9.7 minutes long on average. And this comes from a demo application that VividCortex uses to give sales demos and things like that. This is a full table scan on a table that's growing and growing. At some point, this became impossible. Like the average latency became really long because this is an intentionally broken application. The other thing that you can do, so that way you'll find long, things that are long on average, which is useful, and you will find stuff that needs to be fixed. But when something is fast on average, but occasionally has some outliers, the 99th percentile is a better way to find out whether some customers are having a bad experience. So you can profile by the P99 of latency. Mathematically, that's kind of like very squirrely thing to do. What does it mean to average and sum and sort by the P99 of latency? So P99 as a metric is problematic in some ways, but it still gets you useful answers, even if it isn't, correct with scare quotes around it. And when you're finding something like on that screenshot from before, you have to answer the question of, is this worth my time? Should I look at this? Should I try and figure out whether to make this better or not? Or is this, not worth my time? And my rules, I'm going to change this slide to get away from rule of thumb, by the way, because it turns out the origin of rule of thumb is not a very nice rule at all. I learned that relatively recently, and I apologize I didn't fix this slide. My heuristic is to conserve resources if your goal is to reduce load on the system and reduce interaction between different systems that are customers. Look at the percent of total. So look at the things that are adding the most aggregate workload to your system. And to make customers happier, look at the P99, because an occasional bad experience makes customers unhappy, even if most of their experiences are nice. And in order to solve these kinds of things, you have to go beyond the profile and get away from those rows in the table down into the original requests that were rolled up into those rows. The aggregate data is great for pointing you in the right direction and telling you prioritize this one or deprioritize this one. But there are no averages, there are no typical requests. They're all, when you look at individual user experiences, you learn so much more. And so you have to drill into something, whether it's the original query log or, again, just my bias is sampling. So at VividCortex, we generate the profile from every request, and then we sample some of the requests, and then you can click from the profile and drill into a scatter plot of the requests, which I've got a picture of. There's a couple of nice things about having samples and visualizing them. There's nothing aggregate about these little circles. Each of these represents one individual real request that actually happened, and so you can click on them, highlight them, and drill them in. So that's really useful. You can see, the actual SQL with all of its parameters and things like that, or whatever if it's, MongoDB, obviously it's not SQL, but you can still see the original request, the query. So that's really helpful. The other thing is that by visualizing them, you can see that there is a story a lot of times you wouldn't see otherwise. For example, a really common thing, like this one's pretty weird, and if anybody wants to guess at why there's sort of diagonal lines of requests, I'd be happy to answer why that might be. Another thing you'll often see is that these latencies are not evenly spread, so latency is vertical here. Higher latencies go higher up on the chart. But you'll see that a lot of things are clustered down and around very tight latencies, and then you'll have occasional outliers. A lot of times you'll often see that there's like a particular band of things that sort of cluster like halfway up the chart or something like that. And you can speculate about what those things are. There is no pattern without meaning, you know. So wherever there's a pattern, there's something that it explains. Thank you. So, you know, drilling into these things can help you understand the story behind this pattern. And then once you dig into them, how do you fix a bad query? If a query is too slow, what do you do about that? You have to answer some questions that you can only answer with human judgment and experience, knowledge of your systems, experience gained from, you know, optimizing lots of queries, things like that. So you can answer questions like, should this query be faster? Or in the case of my full table scan, that was 9.7 minutes or whatever that was. That query is as fast as it should be for scanning the whole table. Can I make it better? Sure. I can purge the table, or I can put an index on it, or I can put a limit on it, or something like that. So I can make it faster, but I have an explanation for why it's slow. But a lot of times I might not have an explanation, like this query should be fast. That's something that we often hear from folks who have application-focused monitoring. You know, I drilled down into my APM tool, I found a slow transaction, a slow page load, or something like that. I drilled down to the bottom of the stack trace, and I found a query that ran for 10 seconds, but it's a single row primary key lookup. It should have been, you know, a millisecond or a fraction of a millisecond, but it took 10 seconds. Why did it take 10 seconds? And this is where that holistic view can really help you, because if you see that there was another long-running query at the same time that maybe didn't come from that application, maybe it came from even something like a business analytics tool, like somebody connected Tableau to the production databases. You know, these kinds of things happen. But you have to answer whether this query is, you know, rationally slow or irrationally slow, and what it should be doing. And then you kind of apply this method recursively to the parts of this query's execution. So you can drill down into the query and ask, what does it take to execute this query? It has to plan, it has to do an index scan, it has to do all of these kinds of things, and which of those are the candidates for eliminating work, reducing work, or doing the work faster? When we look at specific technologies, so all of this has been pretty technology agnostic, but we do get into specific technologies, and they always have their own special resources. InnoDB has the buffer pool. MongoDB has, depending on the version, has locks. You know, actually, I guess the Achilles heel of MongoDB these days is indexing, because queries, you know, it's just something that people stumble over really commonly. That MongoDB just tends, sort of culturally, to accumulate a lot of workload that has no indexes to make it faster. And so there's always something that is either a sharpness in the technology that trips you up, or something about the culture and kind of the ways of using it, or maybe it's, you know, your framework does this by default or something like that. There's always something that ends up being that typical problem that you overlook until you find it. Okay. And there's always a technology-specific resource that's kind of a problem as well. So connection pools, a fixed number of connections, that's a resource that you can exhaust. Caches, the algorithms around caches, the query cache in MySQL was a huge, huge problem. Eventually, they just removed it, you know, because there wasn't a good way to make it better. So there's only a handful of things usually that matter a whole lot, but it depends. And there are ways to get kind of like a good head start on this. Vivid Cortex, for example, has a bunch of heuristics built in. We call it best practices, and it's under the health section. You can go there and find out things like, my configuration has a common mistake in it. Just this morning, was meeting with a customer who said, you know, I came from a different database, not super familiar with MySQL. I didn't know that it has a default setting for how fast it thinks the disk is, and it optimizes a bunch of algorithms around that. And you know, the best practices pointed him to that, and he found, you know, well, we have solid state drives, so we should set this parameter differently, and it made a big performance difference. So there's always those kinds of things, right? So you have to know your technology, and you can often, there are great wiki pages, blog posts, things like that. So in conclusion, this is kind of my philosophy and approach to performance method based on, you know, this This started before Percona. Then I worked at Percona for, what, 4.5 years, something like that. And together, Peter and Vadim and I spent a lot of time sort of iterating this. And I also look back to people like Kerry Millsap. His book, Optimizing Oracle Performance, and his method are very influential for me. But I've continued to evolve this over the years. Don't really have a name for it. Maybe the Zen of performance. Like to find something not religious. But this is kind of the overall gestalt of where I am at this point in my kind of understanding of performance. So do these things. This is what I do. And I found that it's pretty much foolproof. I guess I'm here, so it has solved all of the performance problems so far. Right? I have some resources. There's some talks that I've given. You can click through to that one. There's some ebooks. This one in the middle is relatively new. A couple of months ago, that one has been flying off the shelves. These are free downloads, and these are clickable images. So if you get the slides, you can look at that. Some other great books that I really like and have a lot of accumulated wisdom. It's influenced me a lot. And you can snap this to grab the slides if you want, and then you'll have links to all of these resources. So I'll wait a second and then go to the next QR code, where I would like to invite you to fill out a 3-question survey and give me feedback on what you liked, what you didn't like, what didn't you understand, what can be better. It's basically, there's like, how good was it, and then 2 text boxes for you to put in whatever you want. And I really appreciate that. So, I have a couple of minutes for questions, and I'm happy to answer, or give you back a few minutes because there's not much time between talks.
Hey, Baron, thanks for the talk. I was wondering about like you mentioned the 7 golden signals, and it is like a couple of them have overlap, like the error rate is kind of in both of them, and concurrency and saturation also kind of seems similar.
Yeah, it's a great question. The 7 golden signals do have a little bit of overlap. So the error rate externally is the number of requests that fail. In the used method, errors is often things that aren't necessarily failures, but are like something that you can get from a diagnostic interface on your RAID controller or something like that. Like it's still working, you know, but it tells you you've got 1 failed disk. Right? So the internal view of errors, you know, the letter is the same internally and externally, but the meaning is a little bit different in those different contexts. And then in the golden signals originally in the SRE book are what is it? Traffic, saturation. Sorry, I can't quite remember it all. But those, I feel like it's often difficult to tell the difference between them a little bit. And the acronyms that I chose here, concurrency, latency, and throughput are all really distinct concepts that are measured differently. And I've given other talks where I talk about, you know, the mathematical dimensions of them, but I didn't want to go into that much detail on this one. Thanks for your question. It's good to see you. All right, I think we should end just so that everybody has enough time to get between talks. So thank you very much. And my contact information is on the slides if you were able to snap the QR code of the slide. So happy to see you at the booth. We have a booth in the expo hall, or just email me or whatever. Thanks, everyone.